I like this gather.town. I feel like I'm in front of a actual hall. I feel just as nervous. Can somebody give me a thumbs up if you can see my screen? It should just be the constexpr init build title. Cool, thanks. Okay, we ready, Odin? Okay, cool. Alrighty, so today I want to talk about the constexpr init build pattern and a library that we built to implement it for primarily for embedded systems, but it could be used in other contexts as well. Some background about myself. I am a firmware architect at Intel, and I work with Michael. Very fortunate that I get to work with him every day. It's this is a highlight of my career right now. We've been using C++ 17 in freestanding embedded since 2020 in our particular group. I personally have also developed the open source tiny FPGA boards and the USB bootloader for them, if anybody here is familiar with them. So what's the problem that we want to solve with this constexpr init build pattern? Well, it would be great if we could build nice modular firmware. But the abstractions that are required to do this can consume too much runtime and memory on embedded systems. Maybe we have a tiny 8-bit AVR or a 32-bit microcontroller with a small amount of memory, or maybe it's a Pico RV32 running on an FPGA out of block RAM, right? So it would be nice to take the really comfortable abstractions that we can write with software on desktops and servers and bring that kind of abstraction down to embedded platforms. So I want to provide an example of how simply initializing services and registering callbacks could actually be computationally expensive on an embedded platform. So I'm going to introduce the concept of a flow. And a flow is going to be a sequence of steps executed in the order of dependency. And for that, I'm not an expert in airplanes at all, but for some reason I chose to use airplane startup. And I know that pilots have some kind of checklist and it takes a really, really long time to pull away from the gate. So I assume there are a whole bunch of subsystems. And each one of these subsystems needs to be checked out, needs to be turned on and initialized. Furthermore, from one plane to the next, there might be different implementations of these subsystems. Different types of engines. And maybe instead of a GPS, your plane only gets a compass. So there's lots of components that would need to be registered, and they might have complicated dependencies in the order in which these things need to be initialized at runtime when you're turning on your system. And there might be multiple steps for each one of them. Another example, referencing Michael's talk and alluding to some future talks, is the concept of a message handler. We have some interface that we are receiving messages on, and we would like to perform actions for specific message types. We need to decode what the messages are, and then we need to dispatch them to the correct module. For example, a 3D printer or a CNC mill has to interpret G code. Those are the instructions that tell the device exactly what to do. It needs to control the XYZ stepper motors. It needs to control the bed heater for a 3D printer, a nozzle heater for melting the filament, potentially extruder fans, the extruder stepper motor, coolant control for a CNC mill, another bed heater, maybe a tool changer, milling tool, etc. There's lots of components here that can process commands that are specifically addressed for those components. And depending on which 3D printer you have or CNC mill you have, they might have one or more of these features removed or additional features that others don't have. And so if you look at the actual G code kind of spec, there's 100 plus G code commands. And if you want to develop this in a modular way, having to search through 100 possible commands to find the right handler would be pretty inefficient. So we would like So the solution is really simple. We perform the entire initialization process at compile time using constexpr functions and template metaprogramming. And I explicitly say template metaprogramming because we can encode really useful type information into the things that we are adding extensions to. We can include things like compile time names. We can include things like abstract syntax trees of domain-specific languages. There's all kinds of really useful things that we can do with that. So if we can preserve that, we get more functionality and we can get more performance. So when I say registering and extending, what exactly am I talking about? Well, I'm talking about the very specific case where we have services. These are things like interrupts, maybe an I2C handler, maybe we're on an SOC and we have an internal message fabric where we can receive messages on. And maybe even we have some internal services like the main loop or some other feature that we want to be able to extend with new functionality depending on which product we're working on. And then on the other side, we have our features. And I am using very, very useful feature names because this depends on the domain. What are we working on exactly? And a naive implementation of this might have our services call directly into our features. And for a small project or simple Arduino project that lasts a few days, that's maybe just fine. And so our CPP files for our services are going to include the header files for the features. But if we have to use real software engineering and we need to maintain this project over time and we need to maintain multiple projects, this should make us sad. This is not where we want to be. This is not modular firmware. So what we need to do is apply the dependency inversion principle. And if you've watched any of Uncle Bob's videos, Robert Martin, or read his books like Clean Code, you would know what the dependency inversion principle is. Basically, we want our high-level concepts to not depend upon our low-level details. And what that means for us is that our features, the things that we're implementing to solve a domain-specific problem, should depend on generic services and not the other way around. An I2C handler is something that we could very easily see using from one project to the next. Same thing with some message fabric handler and our interrupt handlers. And so we want the dependencies to go the other direction. And when I say dependency, I mean the source code dependency. The domain-specific features or the project-specific features should depend on the services that they are using. So our source code gets flipped. Now our feature CPP files are including the feature headers, the service headers. And this makes us happy because we can mix and match different features without modifying our core services that we want to reuse. What does this look like in practice though? Like how do we actually implement the dependency inversion principle from a generic standpoint? Well, let's say we have our GPIO interrupts service. And this is going to be a service that can call something whenever a GPIO interrupt is triggered. Instead of GPIO interrupts depending on the features, it's going to depend on a generic interface. And that generic interface, in this case, is a simple function pointer. Our features also depend on that interface. And they depend on it in order to implement their functionality. So they can register their callback to be executed on their behalf when the appropriate GPIO interrupt is triggered. So we would like to have a library or a pattern that actually implements this for us. what's our wish list? Well, in order to get the modular firmware that we want, we need to fulfill the dependency inversion pattern. We would also like minimal code and data size because we might have to put this on an 8-bit microcontroller due to cost constraints, or even a 32-bit microcontroller, which has a decent amount of memory, but we have very, very tight constraints on how many things we need to be handling and how quickly we have to respond. This is kind of a sliding scale. We would like very much to be able to do template metaprogramming when initializing our services. We want to preserve that type information so that we can do really cool things with it. And I'll give you some clues and hints to that a little bit later. And we really want this to be easy to use. We want it to be easy to use so that it is used and so that it can be maintained over time. So let's start with the observer pattern. The observer pattern is the very simple case, kind of like an interrupt. There is some event that can occur, and when that event occurs, we're going to call all of the observers and notify them that the event occurred. So here we have our handy dandy function pointer. This is our interface for executing the appropriate action, for notifying the observers. And then we have our service implementation, which is going to be a callback. It's going to be called callback. And we can register observers with the add function. And we can execute all of the observers with the invocation operator. When we implement this on an embedded system, we have a few things that we need to think about. Well, we have to store this somewhere. And because we're an embedded, we don't really want to use malloc. We could potentially use an intrusive linked list, but that's kind of not a very happy thing. So we're going to choose to statically allocate some memory for now. We store our observers. We store the number of observers that we've registered. When we add an observer, we just stick it into that array and we increment our pointer, our count. And when we execute it, we just iterate over all the observers and execute all of them. It's pretty straightforward. How do we use this and how do we put this into a real system? Well, we need something useful to do. And so we have a volatile variable, and we're going to do some really important stuff with this. We're going to write zeros to it and ones and twos, and this is going to represent the useful work that we would do in a system because it won't get optimized away. And then we're going to have our different feature modules or components. And they're going to do something that's important, and they're going to register that very important thing with their services. So I want to do some important stuff in main loop. And then we're going to have some other features that also want to be initialized. And somewhere in our project, we have to initialize each one of these features. We have to explicitly call them to say, hey, I want your functionality to be included in this project. And in our main function, we call the init function, and then we execute our main loop. And the main loop is the extension point that we have. It's the service that we're calling. And so we end up calling all of the do stuff methods of our various features. Also, please don't call your functions do stuff. When we compile this, what does this look like? Well, it looks like a lot. I'm using RISC-V because I can honestly read this a lot easier than x86, and I think it's a little bit closer to the embedded world, things that we might have on an FPGA, or maybe future microcontrollers will have more of these. But just registering the observers with the main loop costs us 84 bytes worth of instructions. The while loop and observer invocation is another 44 bytes. The storage for the main loop is 68 bytes. And the observer implementations is 44 bytes. We're not doing a whole lot of stuff here, but we're consuming 240 bytes. And if you're on an 8-bit microcontroller, they typically have a 16-bit address space. So moving pointers around is even worse, and you're using a larger percentage of instructions and memory for that. So if you look back at our wish list, we've fulfilled the dependency inversion pattern. And if we were on a desktop system, we would say, hey, we're done. We did it. But our data encode size is pretty bad. We can't do template metaprogramming when initializing services. And I don't think this one is particularly easy to use, but it's not terrible easy. It's not terrible either because it's kind of obvious what's going on. So how can we fix this? How can we eliminate this runtime overhead? Well, as the name of the talk suggests, we can make it constexpr. So let's take our initialization functions and make them constexpr. And then we need to go and get rid of the global main loop because we need to put that into the main loop, the main initialization function. We can't modify global variables in constexpr context, so we have to pass it in on the function to get that done. And then when we call the init function, it's going to create a local version of the main loop. And that's definitely initialized at compile time. So what does this look like now? It looks way better. We have 12 bytes just to load the literals, and depending on which instruction set architecture you're using, sometimes the compiler needs to do this, otherwise it just can load it inline. And our main loop is only 16 bytes. Everything got inlined. Even the do stuff functions are inlined and optimized away because this is the only place that they're used. We've gone from 240 bytes down to 28 bytes. Also notice we don't even need the data storage for the callback class. We've saved a lot here. So we've fulfilled the dependency inversion pattern. We have minimal code and data size. We don't allow template metaprogramming. Also, I still don't think it's easy to use, but I'm not going to knock it on that just yet. How can we fix this? And how can we actually use template metaprogramming to our advantage in this case? Well, the thing that makes us sad here is we have a fixed size for the number of observers. And you could argue, well, if we need to change it, we can, but we probably won't need more than 16. And then invariably, 2 projects later, you do need more than 16. And when you try to register more things, something breaks. And what is it? And when we have our add function, this is where we actually are adding the things to our array. So let's use template metaprogramming and fix this. Now, we're going to make the callback type immutable. And the add function is a pure function. It doesn't modify the observers. Instead, it returns a new callback that is 1 larger and contains the new observer. If we can use this, then we don't have to worry about figuring out some magic number, and we don't have to worry about exceeding it because we won't. We're also going to be using the optimal amount of storage if this ever happens to make it into the memory. This is good. We're happy. But how do we use this now? How do we add this into our code? Well, it's not going to be pretty. In our init function, since we don't really know what the type of main loop is going to be, we're going to need to use a template function for that. And then in the global init function, we have to pass the main loop that gets returned every single time. So that's not very pleasant. But we have the same code as before. This is very, very efficient. This, however, is not so great. So we're going to want to take a look at this and fix it. We get 3 of our items, but definitely not easy to use. What do we want from this? Well, we want to know what are the services we need to initialize. In this case, we only have 1 service, but it is very easy to imagine that there are many, many services that we would want to have. And each of those services would need to be presented to each of the features. So when we're initializing and putting everything together, what we really want to do is to compose a collection of services and features. Let's look back at our diagram. We see there's a many-to-many relationship between services and features. And we also see that features could extend other features. This can be thought of like extending some existing power-up sequence or extending our main loop and adding something new and it's polling some register or performing some additional work. So we need a better way to think about our services and features and how do we bundle them and how do we compose them into a system. Well, the bar feature is really two things. It has to have a service and it has the feature. The service is something that other things can extend. It's an extension point. And the feature is providing the actual functionality. So we can kind of think of these as a single thing or kind of unify them a little bit by putting them in a component. And we can do that for everything, even if there's just a feature or just a service that can get extended. And to generalize this, our components can contain 0 or more services. And when we have a project, our project is composed of 1 or more components. So this brings us to the CIB library, which actually implements this pattern in a really nice way that gets us all the items of our wish list. And there's multiple parts to this library. We've talked about the services, and a callback is an example of one of the services. We've seen our main function. That's an example of what it would take to support kind of the basic dependency inversion pattern. Now, there's also this concept of builder and builder meta and impul interface, and we're going to get to all of those and describe how all of them work and how all of them fit into this pattern. But first, let's talk about the project. Well, we want to be able to create a project with minimal overhead and the least amount of imperative code, procedural code. We need a name for our project, so we can put it into a struct. And we see we have this config syntax, or sort of a DSL for configuring our project. But ultimately, we have a list of our components. And so we have some boilerplate code that we need to define what our list of components is, but it's very difficult to get this boilerplate wrong. If you get it wrong, if you miss something, most likely it won't compile. But in the other pattern, if you get something wrong and you don't pass the services through correctly, you'll compile, but you're going to be missing functionality that you expect to be there at runtime. So we have a declarative way of creating our project. But what do our components look like now? Well, we can do a very similar pattern with the components. Instead of putting them in namespaces, we can put them into a struct or a class so that we can reason about them and move them around. We have our function for doing the important stuff, and we could have multiple functions. We could have lots of stuff that we're doing that's very important. And we have a declarative configuration that exposes to the library what are we extending and what are we extending it with. And here's a simple example where we have maybe a runtime initialization service as well as the main loop service. So this is a very nice pattern that we can follow. And this should make us pretty happy because the part that is tying into the rest of the configuration is declarative, and it's difficult to get that wrong. For the bar component that has a bar service, we have a configuration command that tells the rest of the library, hey, we are going to export these two services, and these services are going to be available to the other features to extend. So that replaces the initialization functions as well as the foo, bar, and baz namespaces that we saw. There are our features. How do we actually use this and put it together? Well, we're going to use something called the nexus. And the nexus has, as a name, a couple advantages. One, it sounds really cool. And two, the definition of it actually fits really well. Definitely is a connection or series of connections linking two or more things. A connected group or series, the central and most important point or place. All of these apply, and it's pretty nice. The nexus is taking the configuration for the project, and it is providing all of the exported services to each of the features. So every single feature at compile time has access to each of the services to extend it. Our example main function is calling into the nexus to get the service for the runtime init and to call it, and the same thing for the main loop. On the other side are the services. And we have a bunch of new parts here to implement our services that might seem a little bit complicated. But let's go through them one by one and explain what they are. So we have a new concept called builder, and we have this builder meta. Well, we need to give things descriptive names. So let's try builder. A person who constructs, a person whose job, a person or thing that creates or develops a particular thing. Yeah, that fits. And so for anything that is building a service by adding extensions to it, we're going to call that a builder. Instead of using our callback directly, we're going to use this callback meta. And the callback meta describes to CIB how to use that callback, how to use that builder, and what is the runtime interface after that builder is built. So here's our initial type. This is saying use the callback type with the default template parameters. So that'll give us a callback that has a storage of 0. And it's telling us that the runtime interface, the type erased runtime interface, is a simple function pointer. This is really important, but we'll get back to that a little bit later. So how does the builder meta actually fit into this? As a user, how would I use that and why? Well, it turns out when we want to create a service, we need a name for it. And so we use a struct that represents the name of that service, and it simply extends the callback meta for the type of service that it is. We could have a callback service. We could have a flow service, which is like a callback service, but you can add in dependencies and you can take care of those dependencies at compile time. Or you could have something like a message handler service. And there's more, but these are the examples that come to my mind. And this is the type name that we use to refer to the service every time we need to use it or extend it. And finally, we have the builder. What is the builder? Well, this should look pretty familiar to us. This is the callback service that we were looking at earlier with the naive implementation. But there's a couple differences in it. We have the add function like before, but instead of having the callable operator, we have this static constexpr build function. And it's a template function. What is builder value? And why is this function static? The builder value type contains a value field that is static constexpr. So the build template function is able to get a constexpr reference to the initialized builder. So all of the extensions that were added to that builder are now available in a constexpr context, which is really important. And what this build function returns is the initialized implementation to be used at runtime. Why do we need this step? Why can't we just have the callable operator on this directly and use it directly? Well, after we initialize that builder and add all of the extensions to it that we need for the project, there might be some expensive calculations that we want to perform before runtime. And so if we have this build function call at the very last step, it allows us to perform that expensive calculation. And it also gives us the opportunity to do some type erasure. and optimize the data structures. So let's go into a little bit more detail about why we might have expensive calculations after initialization. And to do this, we can look at our example of the airplane startup. There's lots and lots of components here, and each one of these components can have multiple steps that are required to initialize it and get ready for flight. We can also imagine that there are dependencies between them. Before you can start up the engines, maybe you need your power generator to be on. Before you can turn the fan on in the lavatory, you also need the power generator, but you might want to do that really soon. So one of the builder types that we have is this flow builder. We can add callbacks with dependencies. So we have our startup service. And this is an internal service. When we are starting up our airplane, we're going to call it, and we expect it to go through all of the steps necessary to get ready for flight. And let's say the backbone of this startup service is our power. So we're going to initialize our flow builder. This is happening within the CIB library as it's bringing everything together in the nexus. This power feature has a step called start generator. And it specifies that the wait for generator to be stable step happens after that. And then changing the generator to a closed loop cycle happens after the generator is stable. So these three steps are added, and it's explicitly saying they must happen in this order with these dependencies. Now we have another component, and this component powers the lavatories. This is a big airplane. This is a passenger airplane. And it's really important that right after we start the generators, we turn on the lavatory fan. But before we can turn on the engines, we need to make sure that the generator is stable. So after that step, we're going to start the engines. And then we also have a fly-by-wire system. And we definitely need to make sure the hydraulic pump is working, and we want to do a self-test of our fly-by-wire system. And we have to do that after the generator is stable because maybe the pump uses a lot of power. Each one of these arrows is a directed dependency. What we have here is a directed acyclic graph. If there are any cycles, compilation should fail. We can't have a cycle in our dependency tree. After we've initialized our flow with all of the various features that want to add their own extensions to it, we're going to build it. And this build process is going to look at this directed acyclic graph, and it's going to figure out in which order do we need to execute these steps so that all of them are satisfied with their dependencies. It's going to use a topological sorting algorithm. We can do the start generator first, and then the only next option is the lavatory fan, and then it must be wait for the generator to be stable, and so on and so forth. The data structure for the graph would be too expensive to have an embedded platform. And walking through that graph at runtime would take far too long. The build step allows us to create a fully optimized function that implements the entire flow. And it can be done in a way that the compiler can unroll the entire loop and inline every single step into a single function. So we are paying nothing at runtime for this very abstract concept. Another example is the message handler. We could potentially have 100 different messages, each one being handled by different features, or maybe several being handled by features. So let's go through this exercise again. We're going to have our G-code handler service. And in that, maybe it has a UART parser for parsing these commands off of a serial interface. And we have our motor control command. Maybe that is move, fast move, home. We need to control the heaters. We need to control the fans, etc. And once we've gone through and added all of the features that need to process G-code commands, we've finished the initialization process, and we're going to build our message handler implementation. And because we have so many commands, and we need to process these quickly, and for some reason we're using an 8-bit microcontroller, or we're using a 32-bit microcontroller, but there's a lot of stuff that we have to do. We have to do it fast. We have to be precise. We want to decode these commands as quickly as possible. So in the build step, we can put together an optimized data structure. Maybe it's a binary decision tree. Maybe it's a binary search tree. Maybe it's a sorted table that allows us to do a simple binary search on it. But the point is, when we build it, we're creating an optimized implementation that we can use at runtime. This could be an expensive operation, too expensive to perform during our runtime initialization, and too expensive to maintain the memory while we're doing that. And the message handler implementation here would process each message, decode it, and then figure out which message callback it needs to be dispatched to. So now we have this impul interface, and we haven't actually talked about this very much, and we didn't even have this concept in the simpler examples earlier on. So what is this impul interface, and what's it for? Well, without this concept here, it would be impossible for features to call back into services. So right now, a feature can extend a service, but it's not possible for a feature to call the implementation of that service. And the impul interface solves that for us. So to illustrate that problem, let's look at this diagram of the nexus, the project configuration, the components, and the features. The nexus, when we create the nexus, it has to include the project configuration. In order to create the project configuration, that source code file literally needs to include each of the components that need to be added. And the features themselves also need to be included by the components. So if we want a feature to call into the nexus, it's physically impossible. Our include dependencies would be circular, and it just wouldn't work. We need a way to break that circular dependency. And the way that we do this is with the service impul interface. This is a type erased interface. So it doesn't actually depend on any of the compile time information as the services are getting built. Instead, for the callbacks, for example, it's simply a function pointer. And this CIB built template variable contains that function pointer. So our features, if they need to call these, just call this CIB built function pointer, and it breaks the dependency. And then at runtime, we can initialize those function pointers with the correct values. And the way that we use this is simply changing the nexus.builder to CIB.build and calling the nexus init function. But this doesn't actually illustrate why we want to do this, right? We're still calling it within main, and we still have access to the nexus. So what's the point of this? Well, if we have a serial port handler that's going to be processing messages coming in on our UART and dispatching them somewhere, there must be an interrupt service routine for it. And if we really want to implement this pattern, we're going to want to hide the details of the hardware that we're on. And part of those details are, how do you invoke interrupts? And how do you register interrupts? And usually it's a weird keyword on the interrupt function, and then you need to have a vector table set up. And there's a lot of ugliness that's very specific to that microcontroller. Instead, you could have a service that provides interrupt handling. And so you would define your UART interrupt service routine as a function that calls the interrupt service routine on the UART handler. And then you can tell the UART interrupt to add that UART ISR. So anytime the UART interrupt gets triggered, we end up calling the UART handler's interrupt service routine. And then we export our UART handler so that other features can register their own functionality every time a message comes in on our serial port. So let's go back to our original example that enabled template metaprogramming and compare this to what we can do now. Well, now we have our components and we have our project configuration and we have our main file, our main function, everything together in one location. And if we call the builder directly, then our output assembly code is just as optimal as the handwritten implementation of the constexpr init build pattern. And this is using arcv2 ISA, different 32-bit controller, also popular in embedded systems. But our main loop here has 16 bytes. And in fact, our entire image is 16 bytes minus the C++ runtime. But we did mention there are cases where you need to access the built services from your features. And in order to do that, we add the nexus initialization, and then we reference things using the CIB built pointers. And in that case, we have a little bit of initialization to set these pointers. We have our call, or our main while loop, which calls into that pointer, and then the implementation of that main loop. But if we look at the implementation of that main loop, it is still fully unrolled and inlined. And so we're only using 38 bytes still, which is much, much smaller than the 240 bytes that we needed for the naive runtime implementation. And so finally, we have a way to create modular firmware with respect to services that need to be extended that's easy to use and maintain. And I'll assert that it's easy to use because we have a declarative way of specifying how we're extending those existing services, what components are we bringing together, and what services are available. So we have real-world results. The examples in our slide, for example, take us down from 240 bytes to 32 bytes or so, depending on your exact ISA and implementation. We are using this in real code bases, and I wish I could give you numbers, but I can't give you numbers on this. But we have solved a very big problem using the flow and the message handler services in particular that now enables our engineers to work independently on independent components. And we've saved significant runtime and code and data memory in our real projects. The first time I implemented something using a runtime flow, it was unusable. David's asking why I switched ISAs. I switched ISAs because for the CIB library, I needed to do that on our own instance of Compiler Explorer. We want to open source the CIB library, but it's not yet. So I couldn't put that code up on the public Compiler Explorer. And arcv2 was convenient to use. But if we were using the RISC-V ISA for that example, it would have been the same size as the previous RISC-V example. So we use this pattern and library today. It enables us to do things that literally would be impossible otherwise, given our constraints. And we're in the early stages of open sourcing this library. It might be released with a different name, so stay tuned. In addition to Michael's talk here and this talk, we have more talks planned. 2 of them that will be at CPP now up in May, and we'll be presenting or submitting talks for Flow Planner and Interrupt Manager and more to conferences later this year. But I would like to thank everybody for joining me and listening. And if there's any questions, I can I can answer them. So Andres asks, can you keep the compiler error messages in check even with the whole firmware being composed in the nexus? Um, the the API that I presented here is kind of like a 2.0 version that has improvements over what we're using in production. And I made some mistakes in the original version that make the error messages really, really long. For example, the composition of all the components ends up being in every type of all of the implemented builders, which is a pain. Um, this new library solves that, and it basically hides it hides the configuration in those config variables. And when you do that, instead of being in a type list, it's in the config variable. So our type names are much shorter. What about two services which depend on each other? Um, that would be okay as long as the service names are in header files that are available to both of them. So including the header file that includes the service names will be okay. And the runtime implementation interface would also be available to both of those services. And then they can call into each other all that they want. And if anybody's on the live stream and they can't see that question, it's what about two services which depend on each other from Odin? So Andres is asking, do you always have to use the build type erasure, or can services call directly if not circular? Um, if you have access to the nexus, you can call directly into the nexus and you don't have to do the type erasure. And if all of your services only need to be used with access to the nexus, you can just do away with the nexus initialization as well. So you don't have to pay any of that runtime overhead. We do this for our interrupt manager, our interrupt builder, because we expose our interrupts by name. And the mapping of interrupt names to which interrupt number, and then also shared interrupts and which enable bits for which shared interrupt, all of that is in a declarative configuration. And so our code just references when this interrupt name occurs, I want to execute this code. And we actually use the flow for that. We don't use callback for that because there's some cases where multiple features need to register things to be executed for certain interrupts. And we also need to assert certain dependencies. And so for the interrupt manager, I explicitly don't want to erase the type. So I want to use the one from the nexus. And I do that because I want to call some template parameters. When I call the interrupts manager, I pass in the interrupt number as a compile time value so that we can completely inline the ISR in the actual hardware ISR. There's no indirection with function pointers there. So I'll give a couple more minutes for any questions in text, and then I'll step away from the podium so we can chat over video. Thank you very much, Andres. Okay, let's go chat off to the side. Thank you again, everybody.